So hi everyone, thank you for participating to this, as Stefan said, this kind of new, this kind of new workshop, and thank you for NPL for all the organization and logistics. Yes, that's one moment. Okay. Okay. So, oops, going faster than I want. Okay. So I will do a few, this is the overview. So I will be talking about a few radio analysis of the new things that we have performed this year in TrisKem. So this is mainly on applications and on resins that are already on the catalog or are to be on the catalog, and rapid screening methods as well. And a huge part that we have accomplished this year about decontamination and mainly on Cesium resin. Okay. So here we've been using Tk300, Tk400 and zirconium resins for iron separation. In the first place, the iron separation was mainly done on the true resin, and usually the iron was fixed in very high acidic concentration with a capacity of about 2.5, sorry, there's a mistake here, milligram of iron on a 2 milliliter true resin. And there we were trying to see how it would do to use the Tk400 resin followed by zirconium or Tk201 tested for to do this iron separation. So the Tk400 is a long chain alcohol based, and it has a very good retention for iron. This was shown by Peter Ivanov and presented during the last TrisKem users group meeting in 2018 in Cambridge, showing that, as you can see, that on here you have a very good retention of the iron in this hydrochloric acid, concentrated hydrochloric acid solution. And then you see and it's possible to elute all the rest of the elements. So this is very nice because when you are using, for example, in active solution, actinides, mainly most of the elements are eluted, and then you can do a nice recovery of the iron. And here it was also specific for the protactinium element, but this is not the topic today. So we've been doing some testing on this Tk400 resin, and the minimum capacity was established to be about 20 milligram of iron per milliliter of resin. This test was performed using 2 milliliter columns, loaded, preconditioned with 9M HEL and loaded with 1 milliliter of solution of 10 milligram iron per milliliter, again in 9M HEL. And here you can see a picture where you see the coloration of the iron on the resin. So this resin gives very new perspective or options for the iron separation. So here what I'm going to present next is in conjunction with molybdenum and niobium to perform the separation of the three of them, but one that could be used also to do this iron 55 separation somehow. So here for this specific testing that was done in TrisKem, so the idea was to do the separation of iron, molybdenum and niobium in terms of activation, separation of elements. So the idea is first to do the separation from the actinide on the Tk400, again in the 9M HEL. So the load here is in 9M, and then there are different types of rins. So what you can see is that most of the elements are eluted in the first in the first rinses, load and first rinses, and then depending on the concentration of hydrochloric acid, you may or you may not do the separation between molybdenum, iron, and niobium. So what was decided is that dilution would be done in 0.05 mHEl. And in this fraction, most of the iron, the niobium, and the molybdenum are co-eluted. And so the idea after that is to find out how to do the separation of those three elements, because of course what we want is to have them in different and very well-defined fractions. So there were testing done on the zirconium resin and Tk300 resins, and these tests are still undergoing. So the idea, of course, is to use the medium of elution from the Tk400 and load directly on the next resin with this medium, so there's no step in between and it's direct. And here you can see the first test results on these two resins. So on the zirconium resin, it's possible to do the elution after the load and rinse in the same 0.5 mHEl. There is a possibility to elute in first place the iron in a 2 mHEl and then niobium with oxalic acid. So far, we are not seeing the molybdenum, so we do believe that we would need a more concentrated oxalic acid solution to be able to do the molybdenum elution. And this was performed as well on the Tk201 resin. And here, so the iron is still the first one to come out. And then there's some artifact here or some of niobium that is kind of eluted, but very here and there. So here it's more something due to memory effect of the niobium when measured by ICP-MS. So this is something we are checking. And finally, the molybdenum would be eluted in a nice and separate fraction in 1 mHEl and a little bit more in 1 mHNO3. So this is something that we are working on because it looks very interesting, and to do this very clean and neat separation of niobium, molybdenum, and iron. Sorry. Next. So in the past years, we've been doing a lot of development on the technetium-99 separation. In one end, it was for the nuclear medicine, and this is something that will be presented later on by different presentations and Stefan. But also for everything that comes to the decommissioning. So TC99 is known to be difficult to measure radionuclide. It's a 100% beta emitter, so it really needs to be clean in its fraction. And even one wants to measure it by ICP-MS, you still need to do some good and clean separation from the isobaric element. So as I said, there's interest in decommissioning, and the presentation of Isabella will talk about it also later on. So for the technetium-99, we have different resins, the TIVA, which is the very historical one and well-known, Tk201, and from last users group meeting, we can have some very nice work that has been performed by the NPL. There is the Tk202 resin, which is very nice because for the TIVA and Tk201, the load solution is rather acidic, very strong or less stronger. But for the Tk202, what is very interesting is that the load is done, the optimum separation is done with the load in sodium hydroxide 5 molar. So this is the possibility to use dilute alkaline fusion solution of a decom matrix for a direct load on resin. So this is very interesting and very promising. And for technetium-99, there's also the Tk300 Resin, and I'm talking a little bit more about it now. Okay, before that, a little bit more on the Tk202 resin. Sorry, there's a lot of Tk all around, so sometimes it's not so easy. Just for a reminder, this resin is based on polyethylene glycol that is being grafted on an inert support, and is working very good when the sorting out effect is with the NaOH. So there's a good separation between molybdenum, technetium. On this graph, we've been testing with rhenium as the chemical homologue of technetium, because here in TrisKem we cannot use the radioactivity, but we were working with different labs that were using the technetium, showing that there's a good correlation between the behavior of rhenium and technetium. So just this to show you that the very good separation that can be obtained on this resin, and very clean separation. So for the Tk300 resin, this is a resin where the support is scintillating beads. It's been developed by the University of Barcelona with José Garcia and Alex. There's a different type of products that would be elaborated with this resin because it's very interesting. So the first one of them is the TIVA, the TK300, which is similar to the TIVA, but instead of having this polymetacrylic support, there's this scintillation resins. So it's the same impregnated type of process, and it allows for direct measurement of the cartridges after the load on the resin and then measurement on the LSC. So this is very nice because it allows for, you don't have to do this, to perform this elution afterwards, like when you use the TIVA resin, where there's the necessity to elute with very strong acidic solution. Here it just stays on the resin, and it's the full cartridge that goes to the LSC counter. So, and also, so there's also a measurement of the eluate, and this is because the rhenium is used as for the chemical recovery, and the measurement in the waste or in the eluate allows for calculating this chemical recovery and then the activity that has been fixed in the cartridge. So it's very mainly for, I would say, environmental applications. And this year we have produced this resin at TrisKem. So we are very proud of that. We are also having this Tk300 resin that was designed mainly for the cesium and/or rubidium separation. And this is mainly for to separate them from their isobaric element, mainly the barium and the strontium, prior to the ICP-MS determination. So we have made a first resin, Tk300 resin, that was showing very good cesium and rubidium retention and separation from pH 2 to 1 molar of acidic solution from other matrix elements, and mainly you can see from the barium here and the strontium. So really the cesium and the rubidium are very nicely uptaken on the resin, and the other elements are just passed through. So this is very nice, but the thing was only that there was a reduced capacity. So we are working on this resin to see how we can improve the capacity, and so this is something that is under development at the moment. So we are very confident that we can find something to work on doing this kind of separation. Rapid methods. So this is something that is very important in our field, and the idea there is to use the resin and to transpose them into fast methods for screening. So there will be a very nice presentation later on from Phil Warwick on the sticks. I'm sorry, Phil, if it's a bit imaged, but it's like a pH pepper type, but for radioactivity. So you just put your stick in the solution, and it will tell you if you have something active or not, saying if you need to do the measurement or not on this specific sample. So that's very nice. And we are also working on membrane disc, like extractive disc, to ease mainly the water testing. So it's been tested first with the Tk300 and 101 resins for strontium and lead. And the idea there is to have a direct load of the solutions from water samples. And there will be a bit more on this in a later presentation, again by Stefan Wagner. So what we have done here, for why we are looking for developing this kind of thing, is that the idea would be to go with very high flow rates, up to 100 milliliter per minute, which is about 6 liters per hour, with adapting rinsing step. And it's a bit like for the Tk300. The idea there would be, in the ideal solution, to keep the element after rinsing, to have it stick on the membrane for a direct LSC measurement of the disc. So the disc would be dry and then transfer into an LSC vial. So there we've made some tests already some time ago, and it's working very nicely. And if this is not possible to do the direct measurement, the idea would be or to precipitate and then go again for LSC or GPC measurement. So we're working on that as well. And this is something we've obtained on the Tk101 resin, mainly for lead here. So this was not done on the membrane, but it was done on a cartridge, but it already gives a very good idea how it's possible to get the to elute almost everything and keep only the lead onto the membrane. So this is something we are working on. And now going on to decontamination and the Cesium resins. So this year has been a great year because we've been able to internalize the AMP pan and KNEFC pan resins production in TrisKem. So this resin were first developed by Dr. Szebesta at the Technical University of Prague. And so there was a knowledge transfer. And so we've been performing this production and comparison. And so we keep the active component at 75%. The density remains at about 0.75 gram of wet resin per milliliter. And the capacity is about 11 plus or minus 1 for the IMP pan, or 31 plus or minus 1 on the KNEFC pan. And this we've been testing that against the resin developed at CBUT, which I'm showing a very good agreement. So we are very happy with this internalization. So just as a reminder, for the resins, the application is for the measurement of cesium 134, 137. And for their determination in water sample by gamma spectrometry. And there will be a presentation by Mirella later in the session, or right after me, I think. So she will show you about this. And also for the determination of isotopic ratio of cesium 135, 137. And there's a very nice and good publication that was published earlier this year in May, showing how to do that and how to elute the cesium element from the resin. It's also used to remove high levels of cesium 137 before mass spectrometry for safeguards. And so this is mainly more analytical, I would say, separations, but there's also the possibility to do, of course, the contamination of contaminated elements using bulk or large quantities and large particle size. And so we were able also to do this production in larger quantities and in larger size, particle size. And a few weeks ago, we produced about 100 kilograms of the AMP pan resin. And the idea there, so this is something we're very happy with as well. And the idea there is to be able to extend the production to other semi-industrial up to industrial applications. So this development, to be able to do this production of very large quantities with this 100 kilogram, is part of the CLIPS structuring project. So I will just move on to the next. So it's a platform technology we've been talking about already in the last users group meeting in Cambridge. And this is to be able to control and have the choice with a wide range of selectivities for size and diameter, depending on what application and what element or radionuclide is to be retained or fixed. The idea is to have a high content of inorganic compound, and we've been testing things up to 85%. And this is this is also to use very large or various inorganic compounds that would be included into the PAN polymer. So as I already said, we've been doing that with AMP and KNEFC PAN this year for Cesium, but there's also some work that has been done on antimony oxide or zirconium phosphate and titanium oxide. So we are testing a little bit of different types of inorganic compound, and some of them are already tested in a small scale, but the idea is to really put this into a larger scale. What we've seen also is that there's a possibility to use organic compound also embedded into this organic matrix. So this we are working on that as well with very nice results. And when the pH is not compatible with the PAN, or I mean the polyacrylonitrile, then we have also started to look into other polymers that would enable us to extend the pH domain in which the resin can be applied. So this is very something we are working on. And so if I'm coming back here, so the idea is really to do customized resin and find solutions for decontamination of effluents, looking at radionuclides, but also heavy metals or pollutants. And we are really open to collaborate for new development and, of course, commercialization. And so here, these were resins that you've been already hearing about, but with new application, I would say. And the big thing was mainly on the PAN resins that we have really internalized and developed this year with the AMP PAN resin. And for the other development and new resins, so far they were performed for nuclear medicine and radiopharmacy, and they will be presented later and throughout the rest of this meeting.